When you study for the ham license, you learn about something known as the skin effect. Section 5.8 of the 2010 ARRL Handbook for Radio Communications, and probably other editions as well, describes this issue. They note that the resistance of a conductor to AC is different than its value for DC. A consequence of Maxwell's equations is that thick, near-perfect conductors such as metals conduct AC only to a certain skin depth, delta, which is inversely proportional to the square root of the frequency of the current. This skin effect decreases the effective cross-section of the conductor at high frequencies and thus increases its resistance. They then proceed to give a formula, which is shown here, where delta, the skin depth, is equal to 1 over the square root of pi times F times mu times sigma. And all that's under the square root. Sigma is the electrical conductivity of the material of interest, and mu is the magnetic permeability of the material, usually a metal. F is the frequency, and pi is the numerical constant, which is approximately 3.14. In this video, we're going to derive this expression from Maxwell's equations, and then use it to calculate the skin depth for some materials of interest to radio experimenters, including copper, silver, typical earth soils, and cement. Maxwell in the 1860s proposed a set of differential equations that turn out to describe an enormous range of phenomena related to electricity and magnetism. So here are Maxwell's equations in the modern vector calculus notation. And they read as follows. The divergence of D, which is known as the displacement field, is equal to rho, the free charge in the material. The divergence of the B field, which is the magnetic induction field, is equal to 0. The curl of the electric field, E, is equal to the negative partial derivative with respect to time of the induction field. And the curl of H, the magnetic field, is equal to the current density, J, plus the partial derivative with respect to time of the displacement field. This term right here is known as the displacement current, and that was Maxwell's contribution, main contribution to these equations. So again, we have Maxwell's equations here, and then there are a set of what are known as constitutive relations. And these define the current density in terms of the conductivity and the electric field. This is a form of Ohm's law. And they define the displacement field and the magnetic induction field in terms of the electric permittivity and the electric field, and the magnetic permeability and the magnetic field. So in radio, the solutions to all of these equations are periodic in time. That is to say, they repeat with a certain frequency. So we can write the solutions for D, B, E, H, and so on and so forth kind of generically as being proportional to e to the minus I omega t, where I is the square root of minus 1. Engineers tend to write I as J. Physicists tend to write it as I. So the chief implication here is that if I take any one of the fields, say the E field, here I've represented it as X because it could be D, B, E, or H, and you express it as proportional to this exponential, then a partial derivative with respect to time just leaves that function with the minus I omega out in front. And so you can do that then to transform these equations into slightly different form when you assume periodic solutions. So the induction field and the displacement field and the induction field, when you take the divergence of those equations remain the same, but the two curl equations introduce these factors of I omega. So you have the curl of E equal to I omega B, and the curl of H is equal to J minus I omega epsilon E. But then you can rewrite J as sigma E, is just Ohm's law, and you then have the curl of H is equal to sigma minus I omega epsilon times the E field. Well, this term right here can actually be simplified, and we'll see that in just a moment. But the first thing that we're going to do is we're going to take the curl, we're going to take the divergence of the curl equation. And the reason we're going to do that is to show an interesting result that we'll need as we go along here. So taking the divergence of the curl of anything is always equal to 0. Taking the divergence of E, then, we do over here, we're left with this, these constant terms out in front times the divergence of E. But we know that the divergence of E has to be equal to 0. And E is defined in terms of D, so we know that the divergence of D is equal to 0. And if that's true, because the very first equation that we talked about was the divergence of D is equal to the free charge density, then that implies that rho f is equal to 0, or that there's no free charge in the metals that we're talking about. And that kind of sounds a little crazy to begin with until you think about it and you realize, well, what that actually means is that on average there's no net free charge, that the charges that are responsible for conduction drift along at some small drift velocity, and they have a very short mean free path before they then cease to be free, and they will either scatter off other electrons or off ions in the conductive lattice. All right, so the next thing that we're going to do is we're going to take the curl of the curl of E equation, and we do that. This is what we end up with. We have the curl of E equals the curl of the negative time derivative of B. And here we're going to make use of an identity from vector calculus where the curl of a curl is equal to the gradient of the divergence minus the Laplacian del squared of, in this case, E. Now we just showed above that the divergence of E is equal to 0. So we're only left with this Laplacian term, which is equal then to, when you take the time derivative out, you have a factor of minus I omega, so that those minus signs go away, so you're left with I omega mu times the curl of H. Because remember, we defined B in terms of the permeability and the H field. Well, what does that get us? Well, we know now that we can replace this curl of H with one of the previous Maxwell equations, so we end up with the negative Laplacian of E is equal to I omega mu times this, and we can rewrite D as epsilon times E, and so we're left with that, and then we can take an E out of everything after we take the time derivative, which brings down another negative I omega, and here we go. Now, at RF frequencies, it turns out that we can neglect this term in these parentheses. And you can see that by checking it. So if we can neglect this term, that would mean that sigma is much, much greater than I omega epsilon, which is really the same thing as taking, kind of the absolute value of each side. Sigma would then be greater, much, much greater than omega epsilon, neglecting the I when we take the mod. And rewriting that means that we can neglect the second term when omega, the frequency, is much, much less than the conductivity divided by the permeativity. Well, could that possibly be true? And the answer is it is absolutely true at RF. Sigmas for metals, the conductivity for metals, are on the order of 10 to the 7 Siemens per meter. And the permeativity of free space is going to be on the order of 10 to the minus 12 farad per meter. When you divide those through, you end up with omega having to be less than about 10 to the 19 radians per second, which is roughly 10 to the 18 hertz. So 10 to the 18 hertz, that would be a megahertz. So our frequencies of interest will always be less than that. So this is an absolutely fine approximation to make for all radio frequencies. And so now we're left with just this equation of the Laplacian of E is approximately equal to minus I omega mu sigma E. This is a rather simple equation now to solve. And we're going to solve it for a particular case of interest. So what we're going to do is we're going to consider a flat conductive surface, a semi-surface, and we're going to ask how the E field behaves as we burrow down into the surface, in other words, under the surface. So think of a slab of metal. This would be the top face. Up here is air, and the metal goes down in this direction and in this direction and then back into the page and out of the page. So think of this as a tabletop, but under the table is just all metal. And we define a right-handed coordinate system of x coming out of the paper, z laying in the plane of the paper, and y being in the plane of the paper as well. Actually, let me say that a bit differently. Let me say that the tabletop lays in the xz plane. That's the correct way of saying it, and y goes down into the table below the surface. Okay, so we're going to first of all suppose that maybe we put an electrode here and an electrode over here, and we feed AC through this big slab of metal. Or maybe we have an electromagnetic wave impinging down onto the surface. But no matter how you think about it, we're going to suppose that we initially have an electric field at the surface that points at one instant in the z direction. And because we have symmetry going in the x direction and in the z direction, the only variation of this field can be down into the y direction. So we're going to write the electric field now as some function E0 that's only a function of y, and the directionality will be given by this unit vector z hat, unit vector in the z direction. Okay? So what we're going to do now is we're going to assume that the solution of this E field can be written the solution of the differential equation can be written in the form of E0, and the spatial dependence now we're going to assume will be another oscillating function, an exponential, e to the iky, and again times z hat. So we're assuming now that the electric field can be written in this form. And then we're going to substitute it into the equation that we just derived, this, and we're going to find out what k needs to be in order for this form of the solution to work. All right? This is a standard trick that we use to solve these equations. So taking two spatial derivatives with respect to y of this exponential function will bring down two factors of ik. So we're left with a negative k squared e naught e to the iky z hat equals just the other side of that equation that we just derived, this side here, will equal minus I omega mu sigma e naught e to the iky times z hat. And I think you can see then that the e naughts go, the exponentials go. These are you can get rid of the vectors there, and what we end up with then is a very simple condition that k squared has to equal I omega mu times sigma. Well, you take the square root of k, and you end up with k being the square root of I omega mu sigma. And that's kind of a bizarre thing. We don't usually take square roots of imaginary numbers. So it's totally fair game to ask what's the square root of I. And it turns out that the square root of I can be expressed as 1 plus I over the square root of 2. And if you don't believe me, you can try that. You can multiply this you can just multiply this by itself and this by itself, and so this squared should give you I, and when you do that, in fact, that's exactly what you get. So what have we done? Well, we've done a lot of math in a very short amount of time to show that we can write the solution of this E field as E0 times kind of a crazy looking exponential, e to the I times quantity 1 plus I times the square root of mu sigma pi f y times z hat. And notice I've slipped this f in there because f, the cyclic frequency, times 2 pi is equal to omega, the radio frequency. Okay, so we're getting close. Notice that we have the square root of mu sigma pi f, which is what we saw before that the ARRL handbook quoted. So we're just going to massage this around a little bit, and we're going to write now this exponential in, we're going to split up those terms, and the first thing that we're going to do is we're going to have a purely imaginary exponential, e to the I square root mu sigma pi f times y. And that's going to be multiplied by an e to the minus square root of mu sigma pi f times y. Now this is a purely real quantity. Stuff in the square root is positive. Y is going to be positive as you go down into the surface. So this is going to decay away. This is going to get smaller and smaller as y gets bigger. Usually for convenience we just define a delta as 1 over the square root of mu sigma pi f, so that we can write the electric field then as you go down into the surface as z hat e naught e to the iy over delta times e to the minus y over delta. Okay. Put in words, we see that the electric field will oscillate, that's the imaginary exponential here, as one goes down into the surface, but it will also be damped out. It will decrease exponentially as it oscillates as you go down deeper into the surface, and it will go down in units of delta. So when y is equal to 1 delta, we end up with this damping term being e to the minus 1, which is approximately 0.37, or very, very roughly 1/3. But as you go down another skin distance or skin depth, 2 delta, we end up with it being damped by e to the minus 2, or roughly 1/3 of a third, and so on and so forth. So after a very, after a few skin depths, the electric field gets damped out to be very, very small. Well, now that we have E, you can see immediately that you have the very similar expression for J, and you can do similar calculations to arrive at similar results for the magnetic fields as well. So now to kind of the fun part of this, which is what is the skin depth for different materials that we're interested in when we experiment with radio, and at some relevant frequencies. Well, I'm going through a big broadcast band DXing phase right now, so one of the frequencies that I'm going to do this for is 1 megahertz. But then we'll go up a couple of orders of magnitude to 100 megahertz, just simply to make the math easy. So for copper, the conductivity, sigma, is somewhere in the neighborhood of 5.8 times 10 to the 7 Siemens per meter. So at 1 megahertz, that gives you a skin depth of about 6.6 times 10 to the minus 5 meters. which is the same thing as saying 0.067 millimeters. So the skin depth in a good conductor like copper is very, very small. And for silver now, we have slightly higher conductivity. Silver is a better conductor of electricity than is copper. We have a conductivity of about 6.2 times 10 to the 7. And so we get a very similar skin depth at 1 megahertz, about 6.4 times 10 to the minus 5 meters. But at 100 megahertz, that skin depth gets even smaller. It goes down another order of magnitude. So at 100 megahertz, the skin depth in silver is 0.0064 millimeters. Now, in videos 5 and 9, we talked about first the physics of soil conductivity measurements, and then in video number 9, we actually went out into the yard and made some measurements. And the result of those measurements were that for the soils in my location, we got a conductivity of about 4 millisiemens, or 0.004 Siemens. And at 1 megahertz, that means that the skin depth is about 8 meters. In other words, you should be able to receive the AM broadcast band in your basement with no trouble at all. At FM frequencies, at 100 megahertz, FM broadcasts I should say, in the United States, the skin depth goes down an order of magnitude, right? Because you're taking the square root of F, or the square root of 100 is 10, so you're just dividing 8 by 10, so you get 0.8 meters. And then finally, a common building material is cement. And the conductivity of cement wasn't entirely easy for me to find this on the internet, which was a little surprising. I probably wasn't looking in the right places. But the conductivity of cement seems to be somewhere in the neighborhood of 0.1 to 0.001 Siemens per meter. And so if you take that range, then at 1 megahertz, the skin depth should be somewhere between 1.5 meters and 5 meters. So AM broadcast band frequencies should go through cement, a lot of cement, without being attenuated too much. In the case of FM, that skin depth is much smaller, of course. That's 16 centimeters to 50 centimeters, half a meter. So cement will attenuate FM much more effectively than it will AM. All right. Well, so that's the math. The case of cement is particularly interesting, I think. I travel a lot, and when I travel, I like to take one of a couple of the so-called ultra-portable radios with me and listen to the AM broadcast band during the evenings. I noticed on my last trip that one hotel, which is largely stone or maybe cement block, but it's probably about 150 years old, so I'm guessing it's stone, had very good reception after around midnight, i.e. after all the very noisy televisions and other electronics were turned off throughout the hotel. However, the other hotel that I stayed at on this last trip was probably built within the last 10 years, and it's got a very cagey metallic grid in its construction, which effectively makes the hotel a Faraday cage at AM frequencies and wavelengths. So I never get decent DX reception on AM when I stay in that hotel, but the older stone hotel is just fine. Well, this has been a pretty mathematical video, but I thought it was relevant. One hears about the skin depth in different discussions, and it seemed relevant to show where it comes from and to calculate it for a few instructive cases. I've been experimenting a lot with AM broadcast band antennas of late and thinking about the physics of ferrite loop antennas in particular. So parts have been arriving in the mail, and we will have more videos on antenna and related topics very shortly, certainly in the coming weeks and months. I hope you found this video interesting. If so, please give the video a big thumbs up below. And as always, thanks for watching.